don't think he's here yet, but I wanted to recognize Mr. Ralph Blumenthal. Oh, there he is. It's been a while. I'm so sorry for spearheading that effort. Back to the race. So we decided it would be held annually here at Bell Works, the one-time home of Bell Laboratories. And no doubt many of you in our audience used to work here when it was Bell Labs. It so happens that the oval-shaped roads that go around the building are perfect for a very flat and fast 1 mile course. And so we like to say that it's possibly the best records eligible road mile course in the universe. Now, along with the attraction of the 1 mile race, we wanted to include some sort of tie-in to science. So we began small in 2021. There's the Holmdel Horn Antenna, by the way. And that's our 1 mile course. And so we had a single scientific display back in 2021. That's not it. I didn't get a picture of the scientific display, so the second best thing was to show you the start of our open women's race and all these lovely ladies and fast ones. And there would be, let's see, I'm so sorry. So we expanded our attractions in 2022 to include science talks. And there would be 2 talks, one on cosmology and one on nuclear fusion energy. Why those 2 topics? Because they deal with where we came from, or at least how the universe potentially began, and where we may be headed if we can harness the energy that drives all those stars in the universe. So, we were delighted to have these science talks, and they were very well received by the few people that attended. But because the attendance was rather low, being outside in a parking lot, so this is the list of talks that we have had. As I mentioned, we always have one on cosmology and one on nuclear fusion energy. This is what we have today. But because we're outside in a parking lot with no air conditioning, it was a little rough on the attendees. And so this is the first year that we've moved indoors in the what should be air conditioning. They're working on it. But we had one more hurdle to clear. And that was that my running club, the Shore Athletic Club, could not host an event that was separate from the race for insurance purposes. And so I reached out to an organization called Star Astronomy, which is based here in the Monmouth County area. And they agreed marvelously to be the hosts for this talk. And let's give a round of applause to our members of Star Astronomy for doing so. And before I introduce the next introducing speaker, let me mention that there are restrooms both back by the auditorium where you came down the stairs, and also there are closer ones out to the left in the hallway. So at this time, let me introduce to you the president of Star Astronomy, Mr. Robert Nunn.
Thank you, Scott. Star was pleased to be asked to host the Big Bang Mile Science Talks. Star is an astronomy club founded in 1957 to participate in Project Moonwatch, a worldwide network of observers who track the path of Sputnik in order to determine the effect of the atmosphere on satellite orbits. Star now holds monthly meetings that feature speakers on a wide variety of topics in astronomy. The objective of our club is to promote enjoyment and the knowledge of astronomy, so our meetings are open to the community, and we hold regular public observing sessions. At our events with the National Park Service at Sandy Hook, we've had 8 telescopes and over 100 viewers. Today's talks promise to continue our tradition of hosting informative science programs. Our first talk is From Dark Ages to Dark Energy, A Fascinating History of Cosmology by Sarbmeet Kanwal. Sarbmeet is a professor of physics at Brookdale Community College, where he has been recognized for his teaching innovations. He received a PhD in theoretical physics from the California Institute of Technology, after which he worked for many years in wireless telecommunications research at Bell Labs. Sarbmeet is also an instructor for Deep Time Network, an organization whose mission is to orient humanity to an evolving, interconnected universe. Within this context, one can visualize a prosperous and peaceful future. As a member of New Jersey's Monmouth Center for World Religions and Ethical Thought, he founded an interfaith youth leadership program called Mosaic. He was awarded the Earl Thomas Teasley Humanitarian Award for this work in promoting peace building within the community. Sarbmeet is a sought-after speaker on topics that range from cosmology to spirituality, and author of 2 TED Talks, Chaos to Cosmos and Science Reimagined, Harmony Through Awe. Please welcome Professor Kanwal.
Thank you, Rob. Hello. Is it on? Can people hear me? Yes. Oh, okay, great. How many of you here have seen Severance, which is a serial? A few of you have. Well, I'm sure you know that it's shot here in Bell Works. And there's a reason why they do that. This building is a bit spooky and kind of a little weird. So today I got a fresh taste of its spookiness. My wife was here, decided to go to the restroom before the talk, and the doors closed behind her. And they were locked. She had to shout on the top of her voice to attract some attention to get them to open. So that's a new dimension to the spookiness here. But, in a way, it's a good environment to talk about mysterious cosmologies, which is what I'm going to be doing today. So I want to start with a little bit of engagement with you. I'm wondering what you folks think when you think about the whole vast universe. So I'm going to ask you to think a little bit and to give me a word, an adjective supposedly, about what comes to your mind when you think about the universe. Now, the one word that I don't want you to say, and this is just to make you think a little deeper, I don't want you to tell me that it's vast, huge, big. We all know that it is. But I want you to go one level below that and see if you can come up with a word that strikes you as a description of the universe, or maybe a feeling that you get when you think about the universe. Anybody? Yes, Marcos? Expanding, okay. You're a scientist, so you know that. Yes. Oh, okay, so you think of it as a technology? Yeah, and the science as well, right? Absolutely. Yeah, Ralph? Sorry? It's everything. It's everything, yes.
Glorious.
Oh, now that's a new way of looking at it. It's glorious. Yes, Scott?
Baffling.
Mysterious, baffling for sure. Oh, wow. Anita?
Goal-directed.
Goal-directed. Now that's a new one. Like intentional. Okay, all right. Yes? Wow, that's good. Governed by cosmic laws, yeah? So you relate it to time because it's such an old universe. So much time has elapsed. Yes? So, energy, that's a big thing about the universe, is its energy. All right. Did you have something else? Dynamic. Yes, it's always changing. It's dynamic. Very, very dynamic. Okay. Did you want to say something? Ah, that's a good one. It's very organized. In fact, one of the amazing things about the universe is that it's self-organized. And that's one of the things that we are going to be talking about today. Okay, so I'm actually hoping that after this talk, you may have a few new adjectives to think about for the universe than what you might be thinking about today. Okay, so let's first make sure we have the right set of slides here. Oh, good. That's perfect. Okay. What is cosmology? Since I'm going to be talking about its history today, believe it or not, I have come across people that thought cosmology had something to do with cosmetics. You know, you can't blame people for thinking that way. But there's actually a couple of different definitions of cosmology. The one that I'm sure comes to your mind is the astronomical definition that says it's the study of the origin, development, structure, history, and future of the universe. But there's another definition which actually preceded the one on the top, and that is a more philosophical definition of cosmology, and that takes cosmology as a perspective, as a way in which you think about everything around you, the universe, cosmology, the whole world. And so this way of thinking about cosmology is actually very important and still very relevant. And the reason that I say that is because you can't really disconnect the two things. When you think about the whole universe, it is automatic that you would start to think about what is my place in this universe? Where do I come from? How do I fit into it? And so forth. So these ideas are really connected. And I believe that one of the things that has happened in our society today is that we have separated them. And I don't think that that separation has served us well or is serving us well. This is my own personal thinking, but I believe that one of the reasons why so many of our young people feel like they don't have any anchor or that they are lost in some way is perhaps because they have obviously in many cases abandoned their faiths or their religions for whatever reasons, and they don't have anything else that they can get some meaning from. So I believe that it's very important that we link these two things, and that's part of what I'm going to be trying to do today, is to link these two things together. And in fact, in the ancient past, for a very long time, these things were very much linked together. In fact, most people drew meaning in their lives from the stories that they heard while they were growing up, from those people that knew what in many cases, these were creation myths that had been created by the communities in which these people were a part of. And they grew up learning these myths right from the beginning. And those myths gave them something to hold on to, some meaning that they could associate, something that they could use in terms of binding their communities together. Not only did they have this basis on which to build their lives, but they were also able to carry it forward over time from generation to generation. And this is something that we have lost partly because our cosmology today has become so complex and so science-oriented that most people cannot relate to it. And one of my own personal missions is to try and make that cosmology something that is within the reach of everybody, not just scientists and physicists. And if we can do that, I think we can take something from it that I believe is just simply not available today because of what has happened. Okay, so that's kind of what I just stated, that ancient cosmologies were not just about astronomy. They were deeply embedded in the social, cultural, and religious fabric, and they influenced how people understood themselves, their world, and their place in the community. So while I go through the history of cosmology, I want you to keep two questions in mind. Of course, there are many aspects to cosmology, but these are the two that I feel were important to what I wanted to say. So one of them is, where do humans fit into this grand scheme of things, right? It's an automatic question that has always been there for a very long time. And do we have a place at all in that cosmology? And the second one, which I find very interesting, is the question of the supernatural, which I'm sure many of you have thought about. And that is, does the supernatural have any place in our cosmology? So since I'm going to use this word supernatural quite a bit, I want to make sure that you understand what I mean by supernatural. So what is supernatural? One simple way to look at it is it's something which the common rules of nature do not apply to. So it's something over and above. That's why it's called supernatural. It's over and above the natural. And to be a little bit more specific about what this might mean, you can say that something is supernatural if it cannot be known through our senses. And actually, all of these do not have to apply for something to be supernatural. Even if one of these things is true, you could consider the entity that you're thinking about as being supernatural. Typically, we think about something that is not localizable in space, so something that's omniscient, that's everywhere, something that is changeless. Everything in nature changes all the time, but something that is changeless and timeless, eternal. It is not subject to natural forces. We think about something that can defy those forces, go through walls and things like that. And of course, the other thing that is usually associated with the supernatural is the mystery that surrounds it. And that is something that I want you to keep in mind. So this gives us a way to look at science, right? Because that's, of course, what I'm going to be talking about most of the time today. And science could be viewed as the process that replaces the supernatural with the natural. Indeed, that is what science has done to a large degree. But towards the end of the talk, I'm actually going to tell you that this definition, this way of looking at science, has a problem. And so, I'll explain what I mean by that later on. Oh, is that true? Yeah. So I thought that this was... Oh, I'm glad you told me, because I thought that both of them were being used. Okay. Okay. Sure. Okay, got it. That's good. All right, so let's move forward with our history of cosmology, and let's see where that takes us. So, of course, we start with indigenous cosmologies. That is perhaps the earliest record that we have of any kind of a cosmology that we are aware of. And here, I just like to point out a little thing that I think is kind of important. We have a way of looking at indigenous, but I want to tell you that our definition of indigenous is very narrowly focused. Each one of us is in some sense an immigrant, because if you look far enough, all of us have moved. Well, we know that our forefathers all of our forefathers were in Africa somewhere, that all of us have moved, so we are all immigrants in that sense. But I also want you to understand that there's another way of looking at it, and that is that we are all indigenous. We are all indigenous to our planet. And so when we talk about indigenous, I'm not just talking about Native Americans or anything like that. I'm talking about our past, all of our pasts. So one of the things that set apart the cosmologies that were created by indigenous people a long time ago were that they demonstrated a kind of an equity in the sense that everything was kind of at an equal status. Animals, plants, humans, they were all important. They were all interdependent on each other. And when we talked about creation, the creation always involved animal spirits and so forth. And so it was a very kind of a non-hierarchical way of looking at things, which, as you will see, changed. So what changed it was about 5,000 years ago, a new idea emerged, and that was the idea of monotheism. So that idea was that there's not a multiplicity of spirits that are completely, filling up the world, but there is one important entity that can be used as the source of all creation. So these monotheistic ideas evolved both in the East and the West, but they took on different flavors. So in the West, what happened is that we developed a hierarchical cosmology where there is a powerful being that creates the world. And the world then is a picture of imperfection while the creator is perfection. So there is a dichotomy here between perfect and imperfect, between good and evil, and that sort of creates the narrative and the story that all of us, even to some degree, are familiar with. On the other hand, something a little different happened in the East. There is still some kind of a hierarchy in the Eastern way of thinking as well. But one thing that is different is the idea of non-dualism, which means that you don't need to think about a creator and the creation. Especially in the Hindu thought, the creator becomes the creation. There is a transformation process that takes place. In fact, it is believed that Lord Vishnu actually created the world by transforming himself into that world. So it's a different way of looking at things. It's certainly not as hierarchical, and it doesn't have that disparity that was created in the West. Okay, so now I'm going to kind of shift a little bit from talking about creation, which is of course a very integral part of every cosmology, to talking about the model of the universe on which a cosmology can be based. So if we are to get a more authentic view of how a universe is created, we first need to understand what exactly the universe is. And that is where science has been an incredible help. In fact, that is in some ways the biggest function of science, in my view, is to help us understand that world. Okay, so let's start right from the beginning. So the very first model that I'm showing here, I'm sure there are many others in different parts of the world as well, but the one that I'm showing here is the Hebrew model, which dates back to 3,500 years or so. And what's interesting about this model, it's of course very fanciful, it's very imaginative, there's not a lot of science in here, but it does at least try to put things on a more natural level instead of a supernatural level. For example, the way that rain was explained in this model is that there's some kind of a dome on top of our world, and and little holes are opened up, and that's how rain comes in, and so on. So there was an attempt to make things more natural, even though they were not based on any kind of a science at that point. So the very first time that science comes into the picture, by the way, the creation story that goes with this particular model is, of course, the book of Genesis that comes from the Bible, which I'm sure you're all familiar with. But what brought science into the picture is really the Greek world, which dates to about 2,500 years ago. One of the reasons why the Greeks were able to really develop science as compared to all the other civilizations that existed at that time is that they were a non-agricultural society, because even if you look at Greece today, you can't grow anything there. It's all rocky and hilly and so forth. So it turns out that when you have agriculture, you have hierarchies because you have to manage and take care of all the resources, store them, and so forth. But in a society like Greece, that hierarchy did not exist, which means that there was a greater spirit of inquiry, a freedom to do that, and that, I believe, was one of the reasons where the Greeks moved forward while the others, couldn't have gotten to exactly that point. So here is the first Greek model of cosmology that was generally, promoted by Aristotle. It was based on ideas that existed about 200 years before the 4th century when he created this model. But what's interesting about this model, it looks at the whole universe in terms of spheres inside spheres inside spheres, and it allows us to actually give reasoning as to why bodies fall, why they move in certain ways, why air rises up. And even though we don't believe that any of that science that was created by him is true today, but it was something that was based on the idea of observations of science. And what it did also do was it tended to push the supernatural outwards from the center of the universe. And that is the edge of the universe, as you can see, says sphere of the prime mover. That is what Aristotle called the unmoved mover, so that was kind of a concept of God, and that then creates all the rest of the stuff that is underneath that outer sphere that he had. So one of the interesting things about the creation story here is that Aristotle himself believed in an eternal universe. He did not believe that there was any need for it to be created, though other Greek philosophers did not agree with him. So they had their own creation myths that were very much like or related in some ways to the gods that the Greeks had and the intrigue between those gods. And so very, very complex mythology there. Now let me illustrate a few things that I'm going to tell you again and again as we evolve from one model into another model into another model. And that is that there are certain things that happen. One of the things is that when people have a fair amount of certainty about a model, they start calling it a standard model. Now it's a little bit cocky because we know that science always changes, and so to call something a standard model is perhaps not always a good idea. But that's what happens, and that makes an establishment around that model that becomes very difficult to crack. So in this particular case, it was kind of obvious that there were deep problems with Aristotle's model. And the problems had to do with the fact that they could not explain very well how the planets moved. They explained the movement of the sun and the moon, but the planets had different motions, and it was very difficult to explain that with Aristotle's model, to the extent that in 150 CE, Ptolemy actually rewrote the model, and he had to introduce 31 little epicycles inside all of these orbital motions in order to explain the observed movement of planets in the sky. So what this indicates is what I call the development of scientific orthodoxy. So while we pride science in being something that is open and always ready for change, the truth is that there is an orthodoxy within science as well. And it was very obvious from this particular thing because it could have easily been shown that the better way to build a model was to put the sun in the center, not the Earth, because that would then explain all these weird motions that the planets had. But people didn't want to do that. One, because they had an authority that they respected, which told them that this was the model. And the other thing is that when you have a model, you can build some narratives around it. And when you have a model which has the Earth at the center, it's a great way to build narratives because that means that we are the focus of attention of the universe. The universe is there for us. It is basically doing all the things that it does in order for humans to populate Earth. And that's a narrative that once it's created, it takes root and it's very difficult to change. The third thing that can happen is that when other people who are outside of this established way of looking at things feel threatened in certain ways by whatever it is, then there can be a backlash and people can actually go and try to reverse the progress that has been made. A little bit of that might be familiar today as well. And so you want to actually go backwards, and that's what happened with the Greeks as well as the Romans, is that when the Roman Empire fell, the barbarians made sure that all the books were burnt and that all trace of what had been learned for these 400-500 years would be removed. Luckily for us, some of that information leaked into places like the Arab world, from where it traveled to India and China. And as a result of that, some of the knowledge that the Greeks had created did not go away. So this is where I connect with the Middle Ages or the Dark Ages, and that is the time when all of this regression happened, at least in the Western world. Okay, so continuing forward, we move on now to what happens after the Renaissance starts to take form in Europe. And what happens here is that some of that knowledge from the Greek learning is brought back into Europe. And this time, the church takes a look at it, and the church, the Catholic Church, decides that it fits in very well with the kind of mentality that they, or the kind of the picture that they had been created in terms of their narrative about our world and about God and so forth. So the church then adopts the Aristotelian model and makes it into their dogma. Okay, so now it becomes very difficult for science to move forward. Because what's going to happen here is that the 2,000-year-old cosmology that put the Earth at the center is now becoming more and more obvious, had some serious problems with it, and people want to do something to change it to something else, and the church doesn't like it. So Copernicus was, of course, the one who first introduced the idea of a sun-centered universe, but he was greatly opposed. In fact, it took him 33 years to get the strength to actually publish his work, with the support of a few of the friends that he had. But once the cat was out of the bag, there were more and more people that sort of started to look into the advantages of this model over the previous one, and so it started to take root over time. Galileo, of course, was the one person that played a huge role in making this move forward. So we now come to Newton's way of looking at our cosmology, which is, of course, a progression from the heliocentric model, the sun-centered model. But what Newton adds to that is the understanding of how everything moves. He introduces the theory of gravity, which brings the heaven and earth together, in the sense that up until then, it was always believed that the earth was obeyed a certain kind of laws, which were different from the laws that were obeyed by the heavens. But Newton showed, and this is kind of an example of how he demonstrated it, showing that the same force that makes an apple come down eventually is also the force that makes the moon go around the earth. And all you have to do is to supply an extra amount of transverse velocity to the object. So this was a huge change in cosmology. And Newton, of course, was a very religious man, so the story of Genesis still continued to be the story of creation, at least in his mind, while other people in other places, may have thought about it in different ways. So we now come to what we consider to be the second major standard model of cosmology. So the first standard model, after 1,000 years, 1,500 years, was finally broken apart. And Newton introduced his new model of looking at things. So in Newton's model, the supernatural has now been moved even further. So everything in the heaven can be explained by natural laws. And the only thing that Newton regarded as supernatural was space and time. Because space and time, in his view, were absolutes. That there would be no laws that govern space and time. In fact, space and time for Newton was the container in which God built the universe. And we'll see how that changes over time as well. Wow, it is pretty warm. There we go. So your person never showed up? All right, we'll carry on. I hope you don't fall asleep. All right, so we now move on to the 1800s. So telescopes kept improving, and we were able to figure out that we were just not a sphere of stars that encased the planets and the moon, but in fact those stars form a whole galaxy. And that was done by looking at what we now call the Milky Way, which is that big strand of light that we see up in the sky when it's dark enough, which it never is in New Jersey. But if you look at it more carefully with good telescopes, you find that it's made up of stars. And then you start to understand that, in fact, most of the other stars that you see are just a few stars in 1,000,000 times more stars that lie in the plane of the galaxy. So people figured out that we are actually part of a disk of stars. right? And the few stars that we see beyond that disk are the ones that happen to lie a little bit above or below us, but most of the stars are in the plane of the disk. So once that idea came into the picture, the specialness of the Earth went away even further. Not only was the Earth not at the center of the universe, but even the sun was not at the center of our galaxy at all. It was somewhere midway between them. So any kind of a narrative that you can create about the importance of human beings being at the center kind of goes away at this point in time. So this is now the third standard model, if you will. And the interesting thing about a model like this is with Newton's theory of gravity, you can now see that you don't need any creation process at all, because if you take a bunch of stars and if you make them rotate around themselves, basically, you can show by Newton's theory that gravity will keep moving them forever and ever and ever and ever. No change needs to happen, nothing needs to be created. So this was the time then where there was actually even the supernatural part that involves having some entity create the universe was starting to go away. This really increased the gap between religion and science. And in fact, at this point, there was a very antagonistic relationship that had developed. In fact, Galileo, who insisted on the heliocentric model, had already been put under house arrest, his books were banned, and so forth. So the rift had really grown to that point. But there was a question that was lurking, and this question would change everything. And that's the rest of the story that I'm going to be telling you today. And that question was about whether or not these fuzzy nebulae that people had seen with their telescopes that had a spiral kind of a structure to them, were they inside our galaxy or were they outside our galaxy? That controversy went on for about 10 years until the astronomer, whom I'm sure you're familiar with, Edwin Hubble, actually used his telescope and a technique to measure distances that had not been available to people before them. He actually found out that one of those spirals, Andromeda galaxy, Andromeda at that time it was called a nebula, not a galaxy, was actually outside the galaxy, much outside the galaxy. It was, 1 million light years away, while our galaxy was known at that time to be only about 100,000 light years. So a whole new way of looking at the universe and its structure developed as a result of that. And now we know that our galaxy is one of 2 trillion galaxies in the observable universe. And this is a picture from the James Webb telescope. Okay, so moving on. So meanwhile, while this was going on, Einstein was busy putting out his own theory about how space and time work. He found out that space and time are not this container that Newton had figured out. He found out that space and time were actually very much like matter. They could be curved, they could be bent, and it turns out that space, time, and matter are so closely related, you can't even conceive of one without the other. So you can't even conceive of an empty space and time with no matter in it. All of it happens at the same time. In fact, space and time are the way in which matter attracts each other through gravity. So space and time are the gravitational field, just like electromagnetism is the field that makes charges attract each other. Space and time is a field that makes masses attract each other. And so that took away even this idea that Newton had proposed of space and time being something absolute. In fact, we now know from the theory of relativity that space and time change from observer to observer. There is no one space and time. Every observer has their own space and time. And so that squeezed out the last vestiges, if you will, of any kind of a supernatural. But there was a little problem. And this problem will grow into something very, very huge. In 1916, Einstein found that the theory implies that the universe cannot be static. He was actually very unhappy about that, because by then the idea of an eternal universe had taken root. And even though Einstein was a maverick thinker, he failed on this little piece, and he wanted to go along with the establishment to insist that our universe cannot be expanding. And so he actually changed his theory to make sure that this would not work, which was he later on found was a big, big mistake. Fortunately, there was one person by the name of Georges Lemaitre who had a very interesting background. Not only was he an astrophysicist, but he had been ordained as a Catholic priest before he decided to take up astrophysics. And so he had perhaps in some ways a more open mind, though one would think that religion tend to be dogmatic and so on. But he insisted that Einstein's original theory was correct, and he then showed that if it was correct and the universe was expanding, then it was obvious and very simple to see that at some time the universe was so small and it would be so dense and hot that there would have to be an explosion to make that universe start to expand. And here is the idea of the Big Bang that first shows up. So this opened a way to calculate the age of the universe, because all you have to do is to figure out when the universe was tiny, or at least like a point. And indeed, he did that by using a whole bunch of galaxies and measuring the speeds at which they were receding from us. And he made a calculation, and the universe turned out to be 2 billion years in his calculation, which was a problem. At that point, it was already known that Earth was older than 2 billion years. So people who were part of the establishment took this as a signal that the Big Bang model was hopeless. It was a wrong idea. How could the universe have started with some kind of an explosion? It just seemed preposterous. And in the undercurrent that was there was also this feeling that if there was a beginning of the universe, then that would mean that we have to be thinking about a creator, and that causes a problem when you have a battle going on between science and religion. So, of course, new theories came up, and one that is most quoted and known is called the steady state model that was proposed by Fred Hoyle in 1948. And that basically did away with the idea of the Big Bang. It said, yeah, the galaxies are moving away from us, but new galaxies are forming within the gaps that are created. So the universe actually stays the same. It never changes. Yeah, sure. So that was a way to get around the observation of expansion. So science orthodoxy was back with a vengeance. People basically rejected the Big Bang model until 1960, when a couple of people in Princeton who were looking for something new to do, and one of them, Dickey, was a very well-known experimentalist, they decided, let's look back into the Big Bang model and see if there's some consequences that we can find that we can actually measure. Indeed, they found that if the Big Bang model is true, that there would be leftover radiation that would basically fill the sky. And they argued that because of the expansion of the universe, the wavelength of that visible light would by this time have expanded to become microwave radiation. And so the idea was that we should look for that microwave radiation. If we can find it and figure out what its characteristics are, then we have a proof of the Big Bang theory. So they started building a detector on the top of the roof of the physics building in Princeton. Meanwhile, something was going on 40 miles down the road in Bell Labs. And in 1960, the first satellite call was made using a kind of a fake satellite, which was a balloon that had been put up into the sky. It was called Project Echo, and it had been used to make the first phone call to talk to the president at that time. And by the way, don't fail to notice the value of the stamp in 1960. So in 1961, the Horn antenna was kind of not really necessary because better technologies had come in to use real satellites. And so Bell Labs, in their wonderful wisdom, decided to hire Arno Penzias and Bob Wilson here to just take this horn antenna and do some astronomy with it, because who knows, something good might come out of it. And we know the rest of the story. So they noticed a noise level that was far exceeding of what was expected, and it was persistent. They tried everything, including cleaning up the pigeon poop, and they couldn't make it go away. Finally, they found out, and they called Bob Dickey, someone told them that he might have something to say about it. And of course, Bob tells the story a lot better than I can. But the rest was history. They found out that what they had discovered was the radiation that Bob Dickey was looking for. And now we know that from that radiation, we can actually make very precise measurements. That radiation originally was thought to be uniform, but when we looked at it more carefully with satellite telescopes, we found that there are minor variations in it, and those variations tell a huge story about how the universe expanded and how it finally came to be the way that it is right now. But there was a big problem here, and this is what will lead to the final standard model that I'm going to tell you about, and that is that when they made the measurement of what the density or the mass energy density of the universe should be in order to justify the size of those little variations, what they found was there was a huge discrepancy. The amount of mass and energy that we have in the universe was 1/20th of what it ought to be if it was to be consistent with all the theories that were known at that time. So thus began a race to figure out where that extra mass and energy is. And looking at all the stars and the intergalactic gas and all of that stuff that they know only accounted for 5% of what was needed. So where is the rest of the stuff? And of course, this is the story of dark energy and dark matter. In the 70s, Vera Rubin, who was a woman astronomer, found evidence for dark matter. In fact, we now know that there is 10 times more dark matter in our galaxy, in all galaxies, than there is ordinary matter, and that forms a halo around our galaxies. And we have figured out many other ways of measuring the effect of dark matter, but we really don't know what exactly dark matter is. And then in 1998, something else happened. While everybody thought that the universe's expansion should be slowing down because mass slows down expansion because of gravity. And so everybody assumed that that would be the case. In trying to measure that slowing down, something incredible happened again. They found that it wasn't slowing down. It was accelerating. And the only way to understand acceleration is to assume that there is an inherent energy that is inside space itself. By then we knew that if that was the case, then that would create the acceleration. So hence came the idea of dark energy. And so now we have a full-fledged description of our universe, even though we only understand 5% of what it really is. The rest of the 95% of the universe is distributed between dark energy and dark matter. We have been searching for that for at least 50 years at this point, at least dark matter, and we haven't found anything at all. It turns out that the standard model of the quantum physics, the particle physics, predicts that there could be things that can create dark matter and dark energy. But all our search to find those particular kinds of things have resulted in failure. We have not been able to find what it is. But this is exactly the mass energy density that was needed, so something is certainly correct with what we have. So it turns out that dark matter creates a scaffolding. To be careful with the time here. It creates a scaffolding that is critical to the formation of galaxies, so it's very, very important. In fact, the ratio of dark matter and dark energy is just precisely fine-tuned so that our universe can either not collapse and become a black hole, or it doesn't expand so fast that everything rips apart. And this gives rise to the fourth standard model, which is the standard model that we have today. It has this funny name called lambda CDM. CDM stands for cold dark matter. Lambda is the name of the cosmological constant that creates the dark energy. And so this explains everything other than the fact that we have to now go deeper into what is it that started the Big Bang. And there is now physics that tells us what started the Big Bang. And we know that right in the beginning there was an order. And this order created space and time. So the order is independent of space and time. It doesn't lie in space and time, because obviously when it was there was no space and time. So space and time gets created at one point, then the Big Bang adds matter into the space, which is where the Big Bang idea comes in. That's when matter gets created in a huge explosion. And then there is a point where light is finally created and fills the space. And this is the light whose consequence we detected in the Horn antenna. And eventually we know that it becomes galaxies, stars, planets, cells, and humans. But what is so amazing about this order, and this is the point where I want to really sort of conclude on my talk here today, is that there is fine-tuning in the laws that generate the order that we have. And this fine-tuning is absolutely essential for life to emerge into our universe. If I change one little knob in those laws, just by a tiny bit, I get a universe that cannot create life ever at all. And that is, of course, a problem because we are here. That's what I just said. And so the original order is fine-tuned for life. It has all the qualities of the supernatural. So the fine-tuning of the original order is always going to be a mystery. And the reason I say that is because, by definition, science does not explain the order of the universe per se. Science explains the order that we observe as a result of simpler order. So science only tells you how to take one kind of an order and from it generate the order that we see in the universe. And then it goes further, deeper and deeper and deeper and deeper. But by definition, science can only start from some order and then explain what comes after that. Science can never actually tell you where that order comes from. And so that original order, which we believe exists, we haven't quite gotten there yet, but we've made a huge amount of progress towards it. That order, by its definition, is something that is not natural. There's nothing natural about it, first of all, because it is the one that creates these amazing evolution history that we know about, but also it is something that cannot be localized in space. It's something that clearly is eternal, is timeless, because time wasn't even there when the order was there. So it has all the characteristics that I outlined in the beginning about supernatural. So what I'm saying is that despite all our attempts to squeeze out the supernatural from our cosmology, we have actually found, or we have narrowed down in some ways, what that supernatural is. And it is that original order. So the fine-tuning of the original order will remain a mystery because science certainly can solve it, maybe something else can. The order does not create the universe, it transforms into it. This is very much like the Hindu mythology, because if you just put that order, it spontaneously generates space. So there has to be no cause behind it. And we understand that from our knowledge of quantum physics, where we find out that things happen without any causes at all. And also the simple order gives rise to more complex order with ever-increasing autonomy, which is why we humans have so much willpower. We can do so many things that maybe other life forms or other objects cannot. So I end here with the answer to the two questions that I started out with. What is our role in the universe? Well, in my view, we are at the leading edge of a march towards increasing autonomy, which comes from more and more order being created. The future of the universe rests on how we use that agency that the universe has provided us with. And you can draw your own conclusions what that really means. And for the second question, what is the role of the supernatural? Well, the original order is the supernatural that has been defined by our science. And we know that it has guided evolution for 13.8 billion years. That's what the original order has been doing. So I leave you with some speculation here. I'm not going to make a statement either way because there's no way to prove something like that. But I leave you with the possible thought that could this source of guidance be something that can be helpful for us as well as we tried to play our role as the leading edge of the autonomous order that the universe has created. Well, my last couple of slides here, basically what I maintain here is that we are far from figuring out what that original order is. As a matter of fact, this wonderful standard model that was created only about 25 years ago, it was at the turn of our century, 2000 or so, that standard model is already in big trouble. It didn't last for more than 15 years, it seems, and we have huge cracks that have developed in it. We now know that what was predicted at the level of the cosmic background radiation in terms of how the universe should have expanded does not match with the way the universe is expanding today. We also know that the constancy of what we called the energy that permeates the universe, we thought that it was explained by Einstein's theory. We now understand that what Einstein's theory tells us about dark energy is no longer holding up to observation. We also know from the James Webb Telescope that we are seeing galaxies very, very early in the universe that shouldn't be there. No theory that we understand can explain how galaxies could have started that early in the universe. So already there are huge cracks that are developing in this model, and time will tell where it'll take us. Maybe it'll take us to yet another standard model. We don't know. But we know that this particular standard model hasn't even lasted more than about 15 years or so. So the mystery stays. And I end with this quote. This is from an astrophysicist. In fact, the data that I'm quoting here about the problems with the model, some of it is only a couple of months old. It was published in March this year. And this particular astrophysicist that works in that location has this to say: the universe might be 13.8 billion years old, but our quest to understand it and our place within it is still in its infancy. Everything in cosmology fit together just 15 years ago in a brief period of tranquility that turned out to be a mirage. The fissures that appeared a decade ago have split wide open, creating bigger rifts in cosmology's favorite model. So we have a long ways to go, folks, but we do understand a lot about the universe that we didn't do before. Thank you. Thank you. Yeah.
We have time for a few questions.
Yes, please. I'd be happy to entertain questions. Yes, Marcos.
I was going to ask about dark energy. The more I read about dark energy, the more I get convinced that what we think about dark energy today is like what we used to think about the ether in the 19th century, something that we needed so things would happen, and then eventually it wasn't there.
Yeah.
And so I'm curious. My question is, what does Dr. Campbell believe in dark energy?
So there are folks out there that believe that even dark matter and dark energy have been wrongly interpreted, that they are some other kind of an effect that has nothing to do with matter or energy. I'm not one of them. I think that there is a lot of evidence at this point that dark matter is something that attracts gravitationally, which is the role of matter. So I think it is some kind of matter. And dark energy, of course, is even a bigger mystery. But we do understand its effects. And so we are now in the process of figuring out exactly how dark energy has changed over the course of 13.8 billion years. And I'm hoping that that will lead us to a new model, a new way of looking at it. But in my own way of thinking, the cat is out of the bag in terms of there being something out there. It's not like ether. You know, ether was turned out to be like a fake, not a fake, but something that people just sort of invented in order to explain something. But no, dark matter and dark energy are here to stay. Yeah. Dark energy too, I believe. Yeah, it's not going to go away because there's something out there that is accelerating the whole universe. It's not a small thing. And we don't understand its nature, but we know its effect very well. And it has to be explained in some way. Yes, down there. Either one of you is fine.
I'm sorry, what would you say is the relationship between dark energy and light? Interface, effect,
Yes.
warning,
Yes.
governs the other, or interacts with
Okay. So dark energy is actually a better label than the dark ages because dark energy actually is an absence of light. So what dark energy, well, that's maybe a better description of dark matter. Dark matter does not reflect light, so therefore it will always be dark. We will never be able to see it because that's its nature, we believe. But dark energy is something a little bit more complicated. But it too, in fact, the reason I think we call it dark energy is not so much because of its relationship to light, but we call it that because it is mysterious. It's dark and mysterious, and we don't understand what its origin are. So yeah, the only relationship with light is the absence of light. That's all. Yes, your question first.
So you mentioned about the JWST finding galaxies that folks shouldn't be there, you know, their formation of the universe. And I noticed the quote up there from the Commandant saying the universe might be 13 billion years old. So these rifts in the standard model, are they really calling the question for our understanding of how old the universe actually is?
Yes, they are, but only in the matter of a few percent here and there. So we're not talking about the universe being twice as old. I mean, again, there are theories on the periphery that claim that the universe is nowhere close to 14 billion years. But by and large, in the mainstream, we believe that we have the general ballpark, but we don't know the exact number, and that's what we want to know. Yes?
Has science been able to determine whether or not they think that in these other galaxies that there is a sun that kind of indicates the movement of that galaxy and potentially light within those galaxies?
Okay. So first of all, the sun is a star, right? It's it's in fact, the sun is a very average kind of a star. So every galaxy is basically mostly stars. That's it. There's a little bit of gas here and there in a galaxy, but our galaxy has 400 billion stars in it. And every galaxy is of that order. Some have 2 trillion stars, some have maybe only 100 billion stars. So yes, there are stars like the sun in every galaxy. Maybe what you're referring to, I'm thinking, is that we also now know that there are supermassive black holes at the center of every galaxy. That's something that we learned in the last 50 years. And we believe, we don't understand that those supermassive black holes may in some ways affect the possibility of life in those galaxies happening on one of their planets. But we don't understand that very well. But there are some speculations that those black holes seem to have a role in making sure that life can be generated in a galaxy. Okay, here first. Yeah.
Well, as scientists, we believe that the validity of scientific hypotheses are tested by making correct predictions about observation. Subsequent to the prediction, science is useful to us because we can predict the future.
Yes. Absolutely.
In terms of predictions about observations and actual predictions, the entire Big Bang expanding universe model has approximately between a 0% and a 10% padding average, in the sense that all cosmologists are always surprised. All of the predictions in a quantitative sense have been proven wrong by subsequent observations with better instruments, and the theory has been modified ex post facto.
Can you be specific and tell me one example of where the Big Bang prediction didn't turn out to be true?
The Big Bang, for example, predicts exact values for the abundance of lithium. Those values are unpredicted by observation. They're much lower. It's not a few percent, it's a factor of 20. Helium, the lowest predictions are, the lowest observations are a factor of 2 lower than the predictions. My own research, the surface brightness predictions of the expansion theory are off by quarters of magnitude.
Okay.
You can go down a list, and in terms of predictions before dark energy, for example, that had to be
Okay.
Have a track record in which you're always predicting something that turns out to be wrong, and you have to modify the prediction.
Okay.
Isn't it time to abandon the hypothesis
Okay.
by basic science?
Yeah. So, keeping in mind that I want to give other people an opportunity here, why don't you and I talk about this at the break time? I will just say one thing here, that the abundance of lithium, you're right, in the beginning wasn't as expected, but over time we have found more and more of it in the universe. At this point, in my knowledge, and I could be wrong, but the amount of lithium that exists in our universe is precisely what was predicted by the. We can debate that. So let's do it offline or in the break time here. There was a question back there. Yes. Yes, there are. Right.
Let's say, for example, the mass structure constant.
Right.
Everybody else, that's what gives us the force, the electric force. Okay, the mass structure constant. If you change the statement is, let's let it go. If you change it by just a tiny little bit, we are not here.
Exactly. That's what I was saying. Right.
Okay, prove it. And by that I mean, in your laboratory, in some finite regional space, tweak the fine structure constant and see what happens. You cannot do that. We cannot change the fine structure constant and test.
We can do calculation. We can do calculations, right?
Well, oh yes, yes.
Yes.
That's the statement. You can do the calculation, but test the prediction.
Because yeah.
My argument is this: can you test the prediction? If you change the fine structure constant, this will happen. Okay? Do we agree with that? If you change the fine structure constant, you do the calculation, and this should happen.
Right.
Should not be here.
Right. No, I see what you're saying.
Okay.
Yeah.
Test changing the fine structure constant.
Hmm.
Can you?
No, you can't. I mean, this is not just a problem with the fine structure constant. It's the problem with everything that we say about our cosmology here, because guess what? We have one universe. We only have one universe, and we can't go and test our theories on some other universes, which is a strange situation, but that's what we have. In other cases, you can do all kinds of manipulations in the lab, and you can check many kinds of different things. But we only have one universe, so we have to just, do what we can with what we have and do our best. Yeah.
Agreeing that it cannot be tested.
Yeah. I'm agreeing with you on that.
But then my contention is if it cannot be tested, then it's not a scientific question.
Yeah, maybe so. So, I kind of said that some part of what I'm saying at the end is my own viewpoint, personal viewpoint. So you can take it as that, if you will. But yeah, you are right that there are certain things that we cannot test because we only have a single universe to live in at this time. Yes, I understand.
It's time to start our break. So should I mention what you brought?
What did you want to mention?
Oh, yes. Would you like to mention that?
So in the break, my gracious wife decided that she would provide some cookies and some water. So we have some of that outside as well. Thank you.
So we'll have a break for 10 minutes. Let's be back here at 10:25. And we'll go with our second talk at that time.